I see already the slides from Natanael Alpay. He will be the next speaker, and he will give a talk about, I'll write it down, commutative doubly idempotent semirings determined by chains and by pre-order forests. So go on, please.
Thank you very much, and thank you all for coming to listen to the talk. Today we'll talk about commutative doubly idempotent semirings determined by chains and by pre-order forests. So first, let us begin by what is a semiring. A semiring is defined by the following equations for all x, y, and z. Addition and multiplication are associative. Addition is commutative. Addition has a zero element. Multiplication is an identity, and multiplication has a zero element, and with the two distributive laws. An idempotent semiring is a semiring A such that x plus x is equal to x. In our work, we'll replace addition with join, since A join is a semilattice. A is a doubly idempotent semiring if x join x is equal to x and x times x is equal to x, and A is commutative if xy is equal to yx. Now we'll try to define a CDI semiring, a commutative doubly idempotent semiring, using the semilattices. A semilattice with zero is an algebra such that join is associative, commutative, idempotent, and x join zero is x. A semilattice is partially ordered by x less or equal to y, and a CDI semiring would be of the form A join zero is a semilattice with zero ordered by less or equal, and A dot one is a semilattice with one ordered by square less or equal, and x times zero is zero. And also we have the distributive law for all x, y, and z. An example would be all bounded distributive lattices are CDI semirings, where x, y is the meet, greatest lower bound of x and y. And in this case, both the additive picture and the multiplicative picture would be the same. And we'll later see an example of it soon. So in the work, we look at three subclasses of CDI semirings. Now one could ask, why do we restrict the cases? So while distributive lattices are well understood, the class of CDI semirings is much bigger, and there is no general structure theory. The class of CDI semirings is determined by a set of identities, hence it is a variety. And Kaj and Langer proved in 2017 that CDI semirings are the smallest variety containing all bounded distributive lattices, and S3, which is a three-element CDI semiring that is not a distributive lattice. And just to show how many more CDI semirings we have compared to distributive lattices, we can see that even at size 8, we have significantly more CDI semirings compared to distributive lattices. So the first restriction would be this restriction of height. And the height of a semiring is the longest chain in it. So when we restrict the height to be less or equal to 2, we have the following theorem, which states that there are up to isomorphism 7 CDI semirings of height less or equal to 2. And as we see in the picture, we have 7 CDI semirings, but one could note that the first 4 only have one picture. And the reason for that is because these 4 would correspond to distributive lattices, where the multiplicative and additive and the join semilattice would be the same. And one could also note that the one at the bottom left is S3. And the proof idea is a proof by contradiction. We simply show that for a semiring of size 2, we cannot have more than four atoms, which are elements between the top and the bottom. And then we get a contradiction. Now we move to our second restriction, part 2, which would be about Catalan semirings. So what is a Catalan semiring? A Catalan semiring is a multiplicatively linear CDI semiring, that is, we have x square less or equal to y, or y square less or equal to x for all x and y. Hence, the multiplicative order is a chain. For A and B such Catalan semirings, we can define the Catalan sum to be the structure over the disjoint union of A and B, which is obtained by taking the picture of A and the picture of B, and connecting the top of A to the identity of B, and the bottom of A to the bottom of B. This would be for the less or equal order, and for the square less or equal, the multiplicative order, we simply take the 0 of A, we put B, and then we put the rest of A. Now we have some example of how do we construct such Catalan semirings, and we should note that for the C, the number at the top is the number of elements, and the number at the bottom is the number in which it was generated by. In the paper by Dr. Jipsen and me, there is a list of many Catalan semirings, and each one of them has a number for the size. And the number in which the elements are ordered would give the multiplicative picture. So in that way, we have two pictures in one. One could also note from the bottom example that the Catalan sum is not commutative, as we get two different pictures. So now when we replace the restriction of height with the restriction that A dot must be a multiplicatively linear, we get the following theorem, which states that the number of Catalan semirings with n plus 1 elements up to isomorphism is the nth Catalan number, which would be 1, 1, 2, 5, 14, 42, and so on, and is given by the formula on the screen. And as we can see at the bottom, we have one Catalan semiring of size 1, we have one Catalan semiring of size 2, we have two Catalan semirings of size 3, and we have 5 Catalan semirings of size 4. And now we have we can see all the Catalan semirings of size 5 and some Catalan semirings of size 6. In this case, we do not see the two Catalan semirings that we constructed in one of the previous slides, but they are in the paper. So now let's just show that what we did is actually useful. As we see, the Catalan semirings will describe a relatively large portion of CDI semirings. So it is a relatively useful result in order to understand the structure of CDI semirings. Now we move to our third restriction. So now we restrict B to be a B join 0 to be a Boolean semilattice, and an atom is an element that is immediately above the bottom. We denote the set of atoms of B by AT of B, and B is atomic if every non-zero element has some atom below it. So now we define a complete lattice and semilattice. A joint semilattice is complete if the join of S, the supremum, exists for all S in B, and a lattice is complete if the meet of S, the infimum, and the join of S exists for all S in B. Now we'll define the notion of quantals that we'll later on use in order to generalize the work. A non-associative quantal B is a complete joint semilattice with a binary operation that such that the multiplication distributes over an arbitrary join. The lemma in the following slide, shows that the result works for non-associative, non-unital complete atomic Boolean idempotent semiring, also known as non-associative atomic Boolean quantals. So now for such atomic Boolean quantals, non-associative Boolean quantals, we can define the Turner relation R on the set of atoms of V by R x y z if and only if x less or equal to yz. Then we have the lemma. We can, using the same R defined on the set of atoms by R x y z if and only if x less or equal to yz, but we should note that we use x as our output variable, which should be determined by y and z. Then for all B and C in B, B times C would be the join of x such that R x y z holds for some y less or equal to B and z less or equal to C. And suppose that R, which would work on the set of atoms, is a Turner relation on the set A, and define B to be the power set of A arbitrary union and dot, where for y and z inside the power set, y times z would be the set X such that R x y z holds for some y in y and z in z. Then B is a non-associative atomic Boolean quantal. Now we split associativity into two inequalities. We have subassociativity, which means that xy times z is less or equal to x times yz. And we have subassociativity, where xy times z is greater or equal to x times yz. Keeping that in mind, we let B, we have the following theorem, which states that let B be a non-associative atomic Boolean quantile with R defined on the set of atoms A, which is the AT of B, as on the previous slide. Then B is multiplicatively idempotent if and only if R x x x and R x y z implies x equal to y or x equal to z. It is subassociative if and only if R u x y and R w u z implies that there exists V such that R v y z and R w x v hold, and right unital and left unital are given by the following two equations. Now, R is said to be commutative if R x y z is equivalent to R x z y, and R is commutative if and only if the corresponding quantile is commutative. We now observe that multiplication is idempotent when the ternary relation can be replaced by two reflexive relations P and Q, corresponding to each case of the formula R x y z implies x equal to y or x equal to z, as we saw previously, and we'll now define P and Q in the next slide. So we have the following lemma that we'll use in order to define P and Q. An idempotent ternary relation R is definitionally equivalent to a pair of reflexive binary relations P and Q via the following definitions. So we can define P and Q from R by Pxy is equivalent to Rxyx, and Qxy is equivalent to Rxxy. And now we can define R using P and Q such that Rxyz is equivalent to x is equal to y and Qyz, or x equal to z and Pzy. Now we can note that if R is commutative if and only if P is equal to 2, and in that case the structure would be given by single relation Q. So now we have the following theorem, but an idempotent ternary relation R is subassociative if and only if the corresponding reflexive relations P and Q satisfy P transitivity, which means Pxy and Pyz implies Pxz, PQ forest, which means that Qxy and Qxz implies Qyz or Pzy, and Pxy and Qyz and x not equal to y implies Pxz. Now, to characterize subassociativity, it would be enough to exchange P and Q, and then we would obtain respective three new equations. And then R would be associative if and only if P and Q would satisfy all six equations that we get, which would mean in an if and only if relation that B would be an associative atomic Boolean quantile. So now, before we move to our main theorem, we can a preorder is a reflexive transitive binary relation. A partial order is a preorder that is antisymmetric. A forest is a partial order such that Pxy and Pxz implies Pyz or Pzy, i.e. all the elements above a given element are linearly ordered. A preorder forest is a preorder such that Pxy and Pxz implies Pyz or Pzy. A forest can have many connected components. Each is a tree. If each tree has a top element called a root, then a forest is said to be rooted, and finite forests are always rooted. So now, before we move to our main theorem, we have one last thing to note, is that a preorder forest with singleton root is a preorder forest such that the following equation holds. The point of the following equation is to basically say that we have a top element, and the top element is a single element. It is not a relation, or a bubble, as later on we'll see in the pictures. Now, using these results about Boolean quantiles, we have the following theorem, which is the main theorem of the talk, which states that atomic Boolean commutative idempotent unital quantiles are definitionally equivalent to preorder forests with singleton roots. In the finite case, these algebras are Boolean CDI semirings, And solve finite Boolean CDI semirings can be constructed by enumerating preorder forests with singleton roots. And as we see, now we have a picture of all 22 preorder forests with singleton roots of size up to 4. And we should note that if the preorder forest has no bubbles in it, then it corresponds to a partial order. And if it has a bubble, like this one, then it corresponds to a preorder. One could also note that the first, second, fourth, and ninth one correspond to distributive lattices. So now we have a quick summary of what we saw so far. So we showed that there are 7 CDI semirings with a joint semilattice of height less than or equal to 2. We constructed all CDI semirings for which their multiplicative semilattice is a chain with n+1 elements. And we showed that up to isomorphism, the number of such algebras is the nth Catalan number. And we showed that the CDI semirings that have a Boolean joint semilattice of size 2 to the n are determined by preorder forests with singleton roots. And all of this is also in the paper. But now we can generalize it. So if we move from Boolean quantals to distributive quantals, and we replace the set of atoms by the set of completely joint irreducible elements, and we introduce the notion of PQ frames, in order to extend the main theorem, we can build more CDI semirings. So an element X is completely joint irreducible if X is equal to the join of S, which is the sup, implies X is in S, and we denote J of A to be the set of all joint irreducibles of A, of all completely joint irreducibles of A. And a PQ frame, a W less or equal PQ, is a PQ frame if W less or equal is the poset, PXY and X less or equal to U, and X not less or equal to V, and Y less or equal to V, implies PUV. Then we have a respective equation for Q, and X less or equal to Y implies PXY and QXY. Using this and some more stuff, we get the following. We can build the following. We get the following picture, which, as we see on the left, this would be the Boolean case. However, we'll have more than what we had before, because in this case we'll also consider the ones where the top could be a bubble. So if we look at the previous picture that we had of the preorder forests with singleton roots, we will not have these pictures where we have bubbles on the top. But now that we do accept them, we have them. And then we have all the right part, which we didn't have before. So we basically constructed significantly more CDI semirings. Thank you.
Okay, thanks for your talk. Are there questions? So if there are no questions, I have 1 or 2 questions. You proposed a construction for constructing Catalan semirings by kind of merging or 2 Catalans into a new one. I think it was on slide 7 or 5-7. Yeah. Maybe this question was not only to you, but also to Uli. You also proposed a construction for combining posets. Do you see some similarity between these constructions? Maybe. I read it in the paper, it seemed a little bit similar how to construct a new order out of 2 orders to combine them. Or maybe Peter?
Yeah. It's a good question. Thank you, Roland.
Yeah. You don't have to answer it immediately, but maybe.
It's a question also because we have been looking at doubly ordered sets, right? At 2 posets.
Yeah.
There is lots of interesting work on in this direction, but no, I'm sorry, no. Currently, the answer is no, I think.
Okay, but because I took a short look into the paper, and it seemed to be how some similar, finding 2 orders, and then putting the elements of the one poset below the other one in a certain way.
Yeah,
some kind of it.
I can maybe say a little bit. The parallel series composition of form sets was the one that Uli was talking about, and so that is when the sum there is when you put them next to each other and have no connections, and the series composition is when you put them one above the other and you put all possible connections. And so what we have here is something that's sort of in the middle, and it isn't trying to have concurrency applications yet, but it's unclear.
But you know, there is I don't know if it's famous, but there is a very nice paper by Zoltan Işık and Zoltan Nimet on so-called higher dimensional automata, which unfortunately have nothing to do with what I call higher dimensional automata, but where they consider sets with a finite number of different orders. And then, so in this setting, you can define series parallel posets as doubly, as in a sense of double posets, where the serial composition is just another type of parallel composition, or the other way around.
Interesting.
So maybe the connection between our two works is provided again by Zoltan Işık. It's very often the case.
Okay, interesting. Are there further questions or remarks?
I also had a question. One thing which I'm always wondering about is when I see a set with two different structures is what does it take for an Ekman-Hilton argument, right? So you showed us some examples of CDI semirings where the two relations coincided, right? But do you know what are preconditions for them to coincide? Under which conditions are they forced to coincide, those two orders?
Are you meaning for these ones? I suppose. Well,
for example, those are some examples where the two orders coincide. Yes.
So in this case, it would be that they are distributive lattices. They correspond to a distributive lattice. So it is not all distributive lattices would be CDI semirings, but some of them are. And when they are, they only have one picture. Now, a general case where it will have only one picture, I'll have to think about it a bit, but I'm sure there is a reason. There is a case where you can say that if this exists, then you only have one picture, yes.
So the original Ekman-Hilton argument is that you have two, you have two monoidal structures where the unit coincides, and maybe there's one more condition, and then you can conclude that actually the two structures are the same and they are both commutative also. If you have an interchange law, this is it. If you have an interchange law between the two monoidal structures, then they collapse into one.
Yes.
So maybe there is something similar here. Thank you.
Okay, of the further questions or remarks? Okay, this doesn't seem to be the case, so let's thank the speaker again.